So last meeting, we have discussed heat exchanger. So we'll just run through what we have in this set of slides for the topic on heat exchanger. So we started with the double pipe heat exchanger, which is the simplest of all heat exchanger. So you have a pipe inside another pipe, and your heating fluid is passing through the annular space between the two pipes, the one in the arrow, and the fluid to be heated is on the inner pipe. So here on top, you have counter current flow, and here at the bottom, you have concurrent or parallel flow. So they are on the same direction. Now, other representation of the double pipe heat exchanger could be something like this in reference to the text that we are using. Then we have the shell and tube heat exchanger, which is the most commonly used heat exchanger, primarily because in terms of the design, it's already mastered by the engineers on how well this particular exchanger performs its duty. So for your shell and tube, so you have, in this case, a one shell, two tube set of heat exchanger. So you have this upper tube set here, that's your first tube, and you have your lower set of tubes here below. So your heating medium is passing through the shell. So your shell side fluid is your heating medium, and the fluid to be either heated or cooled is in the tubes or passing through inside the tubes. As discussed, the different orientation of your shell and tube heat exchanger could be 1-to-1, one shell, one set of tubes, or you can have 1-to-2. You have one shell and two sets of tubes. The one that I have shown you is one shell and two sets of tubes. Then we can even have two shells in this case and four set of tubes. But there are even a lot of orientation, as I have mentioned, available in your handbook. Now, you have also learned that in terms of the advantages, you have good mechanical layout as one of them for the shell and tube heat exchanger and the well-established design procedures. Okay, we have the plate and frame heat exchanger consisting of several plates clamped together, and then it has gaskets on the sides. So the key in the design of this particular type of exchanger is in the choice of the proper gasket in terms of the feed that is being processed by the heat exchanger. So this is your plate and frame heat exchanger. So the fluid used as the heating medium is passing between the plates, and the tubes to be heated or cooled are passing through inside these tubes. Now, advantages of the plate and frame heat exchanger is that its temperature correction factor is higher than that of the plate heat exchanger. With a higher temperature correction factor with that of the plate heat exchanger, we expect that your delta T mean will be higher. If the delta T mean will be higher, the amount of heat that is transferred is also high in the case of plate and frame heat exchanger. However, this type of heat exchanger, you have to use only clean fluids. Clean, and also aside from that, it can also handle viscous, highly viscous fluids. You can see it in here. So please take note of the special applications of each of the different types of heat exchanger. So for this one, it's really critical. I mentioned also at the beginning that the gasket that should be chosen is well adapted to the feed that is going to be processed. Now, another is the plate and fin heat exchanger or the matrix exchanger. So similar to the plate and frame, only that this time in between the plates, you have corrugated sheets. So the type of flow that is catered to by this particular plate and fin heat exchanger could either be cross flow, the one you see here on top, or counterflow, the one that you see here at the bottom. So instead of just pure plates all in all through and through, this time you have an alternate of the plate and the corrugated sheets. Then we have the use of that particular type of exchanger. So You can have here that your units cannot be mechanically clean, so their use is restricted to clean, process, and service streams only. Spiral heat exchanger is just like your plate heat exchangers wherein you have rolled the plates that you have stacked one on top of the other. So the fluid flows through the channels formed between the plates that have been stacked one on top of each other. So this is your spiral heat exchanger. Then we have the scrape surface exchanger, similar to that of the double pipe heat exchanger. The only difference is that in your central tube, you have this scraper to ensure that no particular solids or feed material or process material remains on the side of your tube in here. That is to prevent also fouling and even crystallization in the process of the heat exchange process. So there has to be a scraper in the central downcomer, this one, the central tube. Now, as for design consideration, we have started last meeting as to the formula that we're going to use for the accounting for the amount of heat that is being transferred in these particular types of equipment. So we still go back to the fundamental formula of heat transfer rate, which is equal to the driving force. This one, your driving force, your delta T, and your resistance, the summation of resistances if you have several resistances to consider. Now, this is also equal to UA delta T. Now, the delta T that you have here is the delta T mean, wherein aside from just simply using the original delta T lug mean formula, we use the temperature correction factor. So the higher the temperature correction factor, the higher is the delta T mean, the higher is the rate of heat transfer. So the subscripts I that you see on the Q, the capital U, and the capital A represents the inner part of the tube. So I. If it's O, that refers to the outer part of the tube. In here, you have an example. In this particular expression here, you have an example in which both convective, so this is convective heat transfer and conductive heat transfer resistances are being considered. So the resistance offered by the wall, in that case of the pipe, and the resistances offered by the film of the fluid inside the pipe and the film of fluid outside of the pipe are all being considered in the R here, and we're used to writing it as summation of R in the manner we write our heat transfer rate equation. So you have delta T over summation of resistances. Now, if these expressions are equated, then we say that they are equal, and as such, your resistances here is actually equal to the reciprocal of the product of U and A. Because if you write this U and A product in the denominator in the form 1 over UA, then 1 over UA must then be your resistance in the same way that you see it in here. So 1 over U sub I, A sub I, 1 over U sub O, A sub O is equal to your resistance, the resistance to heat transfer. Okay, so this is still our formula. We just add on. So you know already the delta T lug mean from the topic on heat transfer. You just need to add on this particular temperature correction factor. Now, in terms of the temperature correction factor, before we go to that, you have this particular orientation of the delta T2 and the delta T1 based on the type of flow. So this one here on top is for this is for co-current or parallel flow. You have this one, and this is for counter current below. So this delta T2 and delta T1 just exchanges position. So co-current, you have delta T2, delta T1, countercurrent, you have delta T1 and delta T2 in here. Now, there is this confusion I've heard last when we were discussing on the topic of delta T log mean on how you're going to write these particular curves representing the hot fluid and the cold fluid, so that there won't be any confusion or misconception. When we speak of parallel flow, the hot fluid curve is written on top, the cold fluid curve is written below. Okay? We say it's the other way around if it's counter-current flow. So if it's counter-current flow, it's the hot fluid on top still and cold fluid below. However, you interchange the delta T1 and the delta T2. You have the same orientation as to the hot fluid and the cold fluid in the two directions of heat transfer. However, it's the delta T1 and the delta T2 that you interchange. So always remember that since hot temperature is higher than low temperature, then your curve for the hot fluid should always be on top of that of the cold fluid. That way you will not be confused. And always remember that of these two scenarios, the counter current flow is more efficient, meaning it makes use of the delta T more than the parallel flow. That is why you have greater amount of heat transfer in counter current flow. And then you use this as the basis in determining which is delta T1 and delta T2. So in terms of the number line, which comes first, it's 1, then followed by 2. So in terms of the delta T, counter current is delta T1 in here, and you have delta T2 in here. Then just simply memorize that in the co-current scheme, you have delta T2 here and you have delta T1 in here. Okay? Counter current is more efficient than parallel flow. So think of that. Now, in terms of the temperature correction factor that I have mentioned, you need to have all 4 sets of temperature for your hot fluid and your cold fluid. It's inlet and outlet temperature, and you need to determine this Y and this Z for you to be able to get that temperature correction factor. The temperature correction factor is taken from the appropriate table as labeled. So if, not table, diagram as labeled. So if the diagram is good for 1, 2, and 1, 4 exchanger, so then this would be the diagram that you will be using. The Z are for the values of the curves in here. The Y is for the abscissa. The temperature correction factor is the ordinate. Abscissa X, ordinate is Y. So you have a different curve for the 2, 4 exchanger and the other orientations that you can find in your handbook. Now, as for heat exchanger effectiveness, so we have discussed this as well. You cannot actually determine the amount of heat transfer using the UA delta T mean formula if all 4 temperatures is not given, or it's not possible to know all 4 temperatures. So you could see here that this is used when outlet temperatures are not given in the problem, and there is no way that you can find it. So in terms of effectiveness, so we have this particular orientation on how we write our hot fluid curve and our cold fluid curve, or hot fluid temperatures and low fluid temperatures. So hot fluid ara gyapon sa babaw, ang low temperature fluids ara sa dalom. The C sub H here, I have mentioned it also. Your C sub H, capital C sub H, is actually your MCCP for the hot fluid. Your capital CC is the product of MCP for the cold fluid. Anyways, I think it's also there in the other slides. Okay? Now for this effectiveness, this is the effectiveness that we substitute to the equation that we are so used to, the UA delta T mean. So if you're using the effectiveness equation, so this will be our equation now. So you use the C mean, or that's the MCP of the cold fluid, then you multiply it with the difference of the inlet temperature of the hot fluid and that of the cold fluid. This Q, which is the product of these three, which has now the effectiveness, is also equal to this. So all these three Qs are to be equated and they are equal. So whether you get the amount of heat transfer based on the amount of heat transferred or rejected by the hot fluid, or the amount of heat received or absorbed by the cold fluid, that's the same amount of heat that could be solved using this effectiveness equation. Okay? And then your effectiveness for counter current flow could be solved, but it could also be taken from a graph. Now, it could be solved using this formula, and this is the formula that I have written in the very first slide on the computation. And you need also to know about the formula of the number of the transfer units. So the number of the transfer units, though it does not appear here in the formula, but it's needed in the determination of the effectiveness taken from the graph. So the number of transfer unit is UA over C minimum. C minimum being the product of MCP of your cold fluid. So this is your formula for counter current flow effectiveness, and this is the effectiveness formula for co-current flow. Now that doesn't change in terms of the NTU, it doesn't change at all, the formula for it. Now I mentioned that you can also get the effectiveness based on these diagrams. So in the diagram, you need to know the number of transfer unit, and if it's not given in the problem, you can solve for it if you're given the UA and the C minimum, or you can determine the C minimum first, substitute it here in the formula, then use it as a divisor for the product of UA. The NTU you need here on the horizontal axis. The curves that you have here are the ratio of the C minimum to C maximum. The upper curve is for 0, and as you go down, it increases until it reaches 1.0. So if the value of the ratio of C minimum to C maximum is not really exactly as written on the curves, you just approximate. Now, what you have here on the left side is for counter flow heat exchanger. So this one is for counter flow. You can see my, this one is for counter flow, as you could see here. And this one is for parallel flow or co-current flow. So the same orientation you have on the ordinate, the effectiveness, and on the abscissa, you have the number of transfer units. You use this method if the temperatures, the four temperatures are not complete. And actually, class, based on the given, you will know that you will use effectiveness if the problem is giving you the number of transfer units, or is giving you UA and the MCP of the hot and the cold fluid. But number one, the very first thing that is notable in terms of the application of the effectiveness method is when there is no way for you to determine all the outlet temperatures of the hot and the cold fluid. Okay? Now, fouling, we know fouling is the deposition of any undesired material on our heat transfer surfaces. Okay, this may significantly impact the thermal and mechanical performance of our heat exchangers. And it's a dynamic phenomenon, so meaning it's ever changing over time. Now, it increases the overall thermal resistance. So the resistance is increased, and thus it lowers the overall heat transfer coefficient of your heat exchanger. Fouling impedes fluid flow. So hindi maka-flow, gitayo yun ang fluid. Accelerates corrosion. So meaning it damages the material in which your pipe is made of and increases pressure drop across your heat exchanger. If fouling should occur or is to be considered, the problem would specify that you need to consider fouling. If the problem is silent about fouling, then you don't need to incorporate it in terms of the total resistance to heat transfer that you are accounting for. Because in the first place, if the problem will not make mention of the heat transfer coefficient of the fouling materials that causes fouling in your heat exchanger, you have nothing to use. So the problem will make mention of this should it be accounted for. So in the case of scaling, so scaling in heat exchangers, of course, lessens the amount of heat that is being transferred from the medium to the fluid that is to be heated. Another cause of fouling is your particulate or sedimentation. So there are sediments that is incrustated in your walls of your heat exchanger. Another one is corrosion. Okay, this is very common if you have high fluid flow. And then we have chemical fouling in the case of those fluids that are not only undergoing a simple heating process, but also undergoing chemical reactions. So that's chemical fouling. And this is not common to us in here, but in the western part of the globe wherein there is freezing and they have winter. So this is the freeze fouling, as they say it. And then we have biological fouling, the growth of microbes or yes, microorganism on the surfaces of our heat exchanger. So probably microorganism that could withstand high temperature. Okay, that's biological fouling. Now, what are the measures that we can do to address fouling in the heat exchanger? So fouling tendencies depends on the type of the heat exchanger, first and foremost, and the fluid that your heat exchanger is handling. So during the design stage, certain consideration may help minimize fouling experience in the field. So if possible, allocate the more fouling fluid to the tube side. So meaning, ato nga fluid nga nagakos ang fouling, hindi siya dapat mag-flow on the shell side fluid. So dapat dito siya sa inner tube, sa tube side fluid siya. Designed for a fouling fluid velocity of 5 feet per second on the tube side and 3 feet per second on the shell side. This is the allowable velocity that will not cause or that will lessen fouling in our heat exchanger. So tube side is 5 feet per second. On the shell side, we have 3 feet per second. So try to keep the fluid velocity constant as much as possible and allow easy access to cleaning. So if periodic maintenance of the heat exchanger is followed, then this fouling thing could also be addressed because regular maintenance, regular cleaning, of course, will not hasten or will not, shall I say, encourage this particular material to grow on the side of our heat exchanger. In water service, ensure that tube wall temperature is not too high to create salts, salt deposits, or render treatment chemical ineffective. So though we don't want salts to keep on growing on the surface, we want as possible our wall temperature to be not too high. And do not throttle water flows in winter time. So this is during winter. Okay. By the way, what do we mean by throttling? Anybody here? Throttle, I think this was discussed in your fluid flow. What do we mean by throttling? I'm just curious. It's a term that you should be familiar of. What do we mean by throttling? Throttling. Mel, would you know what throttling is? Mel?
Miss, any kind of flow restricting device that causes a significant pressure drop in the fluid.
About the definition. Okay, a simple case of throttling is that you decrease the flow, or there is going to be a restriction in the flow from higher cross-sectional area to lower cross-sectional area. That's throttling. And in the process of throttling, of course, there's going to be pressure drop. Okay, or there's going to be a change in the flow pressure. So, gitagaan na ta ni Mel definition of throttling. Now, in heat exchanger fouling, so this could be the case. You have here a clean inner tube and outer tube. And if you have fouling, so this would be the case where you have fouling. Your inner tube on the outer part is incrustated with scale. And in your shell side fluid, probably, this is your shell side fluid. This is where your shell side fluid is flowing. You have encouraged as well, or an encouragement of the formation of this other scale. So you have this scale here and you have this scale here, and we say that our heat exchanger tubes are fouled. So in that case, we are to consider the corresponding resistances offered by the scaling material. So I think I have shown this last meeting. Your original U sub I, or overall heat transfer coefficient based on the inside area, is just based on this. You have the film on the inside part of the tube, the film on the outside part of the tube, and the tube itself. So this is all convective heat transfer, and this is resistance offered by the tube itself. Now, what do you mean, Miss Ali? You have fluid here, right? And you have fluid here. Oftentimes, the fluid to be heated is in here, and your heating medium is in the annular space. Okay? The material in which this pipe is made of offers resistance in itself to heat transfer from the shell side fluid to the tube side fluid. Okay? So, ini mismo ang pipe may resistance to heat transfer na between these two fluids that we are considering. The formation of scales here or fouling material also offers resistance to flow. So, this is for the outer, and if there's another thing here inside, there should be inner fouling as well. So, if you're going to consider fouling, class, you add on this particular 1 over heat transfer coefficient and resistance of the scales, in this case, the scales that appear on our inner tube. So you have one here, it's not drawn in here, and you can have another here, so that's outer. You'll have one inner and you'll have one outer, and this is your tube that is offering conductive resistance also to flow of energy. Let's say from this region to this region here, from the fluid in here in the shell to the fluid in the tube. So, i-account nyo gid na siya ang iya resistance. So, you have two resistances here added. Kung wala man lang, then there's no need for you to account these two resistances due to the fouling. So, what does the fouling do? It increases this, rather it decreases the U sub I. So, if it will decrease the U sub I, your amount of heat transferred also will be decreased based on the formula UA delta T. So the more fouling you add in here, the more that this U sub I will lessen or decrease. Okay? That's our formula. Those are the formulas that we will be using in the following sample problems. So this will be our first sample problem for this afternoon. You are given a 1-2 heat exchanger containing 1 shell pass and 2 tube passes that heats 2.52 kilogram per second of water from 21.1 to 54.4 degrees Celsius. Now, the thing that is being used in heating is hot water under pressure, entering at 115.6 and leaving at 48.9 degrees Celsius. The outside surface area of the tube in the exchanger is 9.3 meters squared. So this is the outside surface area of the tube. Calculate the mean temperature difference, delta T mean, in the exchanger and the overall heat transfer coefficient based on the outer part of the tube. This is primarily asked because that area which is given to you is based on the outside surface area. Now, letter B is just a redo of letter A, but this time you're not using a 1-2 heat exchanger, but a 2-4 exchanger. Now you're just asked for the delta T mean. So in this case, I'd like you to take a picture of the problem that we're going to solve. I go to the Jamboard. That way we will not go back to the same problem while we are solving it. Okay? Okay, 1, 2. So we'll go now to our Jamboard. Okay, wait, class, ha? I have not opened yet Jamboard. I'll just open it. Here we go. Okay, that's our Jamboard. I hope everybody could see. I'll just clear my frames. Okay. Because I cannot anymore add boards here. Already reached my limit. So this is in my last class a while ago. Just give me a few minutes. Okay, so this is our first sample problem on heat exchanger. So I hope you have taken a picture of that particular problem. So on the first statement, you are given already the type of heat exchanger. So you have a shell and tube heat exchanger. Okay. And then this particular heat exchanger is the 1-2 type of heat exchanger. So one shell, two tube passes. Now, for your fluid to be heated, you have water. So the temperature of the water, inlet temperature of the water is 21.1 degrees Celsius, and its outlet temperature is 54.4 degrees Celsius. For this water, you're given its mass flow rate. So it's 2.52 kilograms per second. So inlet temperature of the water that is to be heated and outlet temperature is given together with the mass flow rate. Now this water is to be heated by water under pressure. So I'll just place here the heating medium. So there won't be confusion as to water and water. So your heating medium enters at this temperature. So I will have this then now as the hot water. So inlet temperature is 115.6 degrees Celsius and its outlet temperature is 48.9 degrees Celsius. Now, since I know that this is my heating medium and this is the medium that is to be heated, then I can place already the subscript C here. That way we can have ease of use of the formula that uses inlet and outlet temperature of the hot and cold fluid. Now you're given also the outside surface area of the tube that is to be heated at 9.30 meters squared. Okay? So if you could check the problems that you have taken the problem that you have taken a picture of, is there anything here that is missing? Or is everything here already well placed in terms of the given? So I think everything is in place. So for letter A, you are asked to determine the delta T mean. Okay? And the overall heat transfer coefficient based on the outside part of the tube. Now this one, is on the orientation that you will have. What is the orientation for letter A? It's not needed anymore, the orientation. It's not stated what is the orientation because you have a shell and tube heat exchanger here. We can just have it plotted later on. Now for letter B, instead of using a 1-2 shell and tube heat exchanger, you're going to use a 2-4 heat exchanger. Okay? Now, I have mentioned also, class, I think last sem, that whenever the problem is silent as to what orientation are your heating medium and the medium to be heated is, if the problem is silent about this, then you have to use the counter current flow of orientation. So it should be counter current flow if the problem is silent about it. If the problem is specific as to what type of flow you will use, then you have to use that particular orientation. Now, this same is the requirement in here, by the way. So you have delta T mean and U sub O. So we go now to the solution. So in terms of the required information, the required information is the delta T mean and the U sub O. We'll try to write first the working equation that you could use, okay? Because that is always your guide. So if it's the delta T mean for letter A, then you need the formula that the delta T mean is the temperature correction factor and the delta T lug mean, okay? Now, these two are unknown for now because in the first place, if you want to determine the temperature correction factor, you need to solve for the Z and the Y for you to be able to have the temperature correction factor taken from the appropriate diagram. So as a review, how are we going to start solving this problem if this is our working equation? Let's say equation number 1. Any suggestion from anybody here? What are we going to do first? I'd like to ask Antoinette. Antoinette, what are we going to do first? Antoinette, are you there? Any suggestion on how we're going to start solving this problem since we need to find both the temperature correction factor and the delta T lug mean? What's the very first thing that you ought to do? Antoinette. Antoinette is out. Sige, Rosel. Can you tell me, Rosel, what are we going to do? If you don't have your mic, you can use the chat box, Rosel. So what are you going to do, Rosel? This is actually a very simple problem wherein we are guided by a formula to use. But we need to start off somewhere. I already started with the formula. So with this formula now, what will you do next? Rosel? Are you there, Rosel? Delta T lug mean. If you're going to determine the delta T lug mean, Rosel, what will you do then? What is to be done first before you determine the delta T lug mean? Your delta T lug mean is given by the temperature delta T2 minus delta T1 ln of delta T2 over delta T1, right? So I write here my equation 2. If I will determine this delta T lug mean, what do I need to do then? Because I can't simply have this delta T2 and delta T1 if I don't do this thing. So what will I do, Rosel? Inlet and outlet, miss. What about the inlet and outlet? Would it be of use to me if I'll have the inlet and outlet temperatures only? Okay. Who can tell me what do we need to do because I want to determine the delta T log mean? Kent, Quadra. What do we do, Kent?
I-substitute, miss,
Okay, hindi gani
ang
ka mo
values.
hindi pa gani ka mo substitute. I'm asking for this very important thing. How can you substitute something when this thing is not yet done? Kyle Bacolod, what will you do?
Determine the flow, mas para mabalaan din ang T1 and delta T1 and delta T2.
Are we determining the
Orientation, I mean.
also, are we supposed to determine the orientation in this case since the problem is silent about it?
And mas ma-assume na counter current na orientation.
Sige. So we have assumed already, for example, assuming counter current flow. So what is this that we need to do? Identify the inlet and outlet temperature of the hot and cold fluids. There is no need to identify this one, Mel, because I already wrote it in the given, right? Ara na siya sa given, no? Inlet, outlet, inlet, outlet. So what I'm asking you is very important. What is this that you need to do? Kyle, would you know? What do you need to do? What do you need to do first? Because there's no way that you can have this delta T2 and delta T1 if you will not do this. What is it that you need to do, Kyle? Or who'd like to answer? Maisel, probably Maisel would know. What do we need to do, Maisel, first? What do we need to do? Maisel, would you know?
Get miss ang Z kaguay para mabalaan ang class.
Okay. Delta T lugmin anay iha. Ang delta T lugmin anay aton determine. So kung kinahanglan ta ang delta T lugmin, kinahanglan nyo ni anay ubrahon. Ano ni siyang ubrahon nyo? Get the difference of the temperatures for hot and cold inlet and outlet. You need to do what? You need to draw this, right? Okay, after drawing it, you need to draw the orientation of the hot fluid and the cold fluid temperature. So hot fluid is like this. You said it's going to be counter current. So hot fluid, so you have THI and you have THO. Send your cold fluid, what will happen with the cold fluid? So I will have it as blue because it's cold. So your cold fluid would be something like this. So TCI, TCO. Now, if you have done this already, then you can get the very important delta T1 and the very important delta T2. Have you already memorized this? It's okay if you have memorized this, but if you haven't memorized the formula for delta T1 and delta T2 for counter current flow, it helps that you draw this one. There's no need to memorize if you have drawn this one. You get it? So this is your counter current flow scheme. If you have drawn it like this, then it's easy to determine now the delta T1 and the delta T2. Now, we determine delta T1. So your delta T1 is equal to the difference of the hot fluid temperature. So your hot fluid is entering at 115.6 and the cold fluid temperature. So your cold fluid temperature outlet is 54.4. That's your delta T1. So you have it already there. Your delta T2 is the difference of the hot fluid outlet temperature, which is 48.9, and that of the cold fluid inlet temperature, which is 21.1. Now, correct me if my values are wrong based on the problem that you have taken the screenshot of. Okay, so you will have now the corresponding delta T1 and delta T2, which could easily be plugged in on equation 2. Can you give me the values of these two? Antoinette, can you give me delta T1? So it's 61.2 here. And you have 27.8 for delta T2. So please check the values that I have written here. Okay, then after that, you substitute to equation 2. So from 2, you can have the delta T log mean. Help me out, Jules, in here. Can you please determine the delta T log mean?
Miss, sorry, miss. Ano to, miss? Ganti na to, miss. Connect ko.
What did Joe
Ano to,
say? It's okay,
ano to, miss?
Jules. I'm already computing it. So
Ayun,
42.326 degrees Celsius. So this is your delta T log mean. So somebody wrote in the, okay. So it's 42.326. Please recheck my value. Mel is giving me a different value. So you have the ln of 27.8 divided by 61.2. That should be in the denominator. It should be multiplied to delta T2, which is 27.8 minus 61.2. So my answer is still 42.326. Okay, so that should be your delta T log mean. So thank you, Jules. So that should be your delta T log mean. Now I'm okay with the delta T log mean already. So I'm okay with this. Now I go to the temperature correction factor. So for the temperature correction factor, we go here on the next slide. You need the very important Z and Y. So the Z and Y formula is given also. I think, I'm not sure if I have written it on the slide, but I'll write it in here just the same. So in determining your temperature correction factor from the appropriate diagram, you need to determine the Z. Your Z is based on the formula temperature, inlet temperature of the hot fluid minus outlet temperature of the hot fluid divided by outlet temperature of the cold fluid minus inlet temperature of the cold fluid. Now, we'll place the values there later. I'll just place the formula here. As for the Y, we'll have outlet temperature of the cold fluid minus inlet temperature of the cold fluid. Denominator is the difference of the inlet temperature of the hot fluid in the inlet temperature of the cold fluid. So for the inlet temperature of the hot fluid, we have 115.6. That of the hot fluid outlet temperature, that would be 48.9. As for the cold fluid outlet temperature, so we have 54.4 and its inlet temperature is 21.1. In here, outlet temperature of the cold fluid is 54.4 minus 21.1 over 115.6 minus 21.1. So you will have the Z and the Y values here. Icholo, can you solve for the Z? And for the Y, please solve it, Rosel. Z is 2.0. Y is 0.352. So please check the values that were provided. Okay, now you have the Z and the Y already. So I'd like to go back to our slide. So please take note of the value. Z is 2, Y is 0.352. So this would be the figure that we're going to use. So our Z in the case is 2.0. For our problem, it's 2.0. And our Y is 0.352. If my memory serves me right. So for the 2.0, it's here. You have the 2.0 here. And for the 0.352, this is your 0.3 and this is your 0.4. This is 0.35. It's a little bit, the 0.352 is somewhere here. Okay. 0.352 is somewhere there. Then you read the temperature correction factor, which is somewhere here. Your FT is more or less equal to, so if this is 0.6, this must be around 0.685. Okay, depends on how well you approximate the value. Antoinette, what are you answering here? The 0.74. If it's 0.352 and you have 2.0, so it doesn't reach 0.7. Okay, so it's around 0.685, more or less. Okay, so in this case, your temperature correction factor is based on my reading. It need not be coinciding with the reading of Gian Kuplis, is 0.685. Okay, so we go back to our Jamboard. So in this case, your temperature correction factor is 0.685. So now you will determine the delta T mean. So this is our formula for the delta T mean. So from equation 1, your delta T mean would be just the product of the temperature correction factor and the delta T log mean. So your 0.685, need only to be multiplied to 42.326. So you will have around 29 for the delta T mean. So 29 degrees Celsius. So this is for letter A. Then the next question is, you will have U sub O. How do we determine U sub O? Is it U sub O? Yes, you are to determine the delta T mean and the U sub O. How do we determine the U sub O if there aren't any question on the delta T mean? How will you determine the U sub O? Any suggestion? So you go back to the fundamental equation. So Q is equal to U A delta T mean. Okay? Now, since we're after the overall heat transfer coefficient based on the outside area, so this should be O and this should be O. Now, what then should be the Q that we will equate this with? Okay? We know already. So if I'll check the things that we know this, we know this. So we can find this U sub O based on this formula, provided that we get to know the Q. Now, what is this Q that we're going to equate it with? MCP delta T. So MCP delta T of what, Antoinette? Okay, cold fluid. Actually, it could be the MCP delta T of the cold fluid or the MCP delta T of the hot fluid. So in this case, if you use that of the cold fluid, then you write here C. So I will have U sub O multiplied 2. So we'll use the area that is given in the problem. That area is 9.3. 9.3, and the delta T mean that we got, which is 29. 29. So you will have the mass flow rate of the cold water. Now, by the way, why are we not going to use the MCP delta T of the hot water? Why can't we not use the MCP delta T of the hot water in this case? Anybody? So actually, it could be MCP delta T of the cold fluid or the MCP delta T of the hot fluid. Now, in this case, why are we using the MCP delta T of the cold fluid? Jules, why do you think are we using the MCP delta T of the cold fluid, not that of the hot fluid?
Para may sa humans.
O, ang ginapamangkot ko lang nga, amo gini. O, si Antoinette na lang, kasi Antoinette ang nag-suggest. Why are we using MCP delta T of the cold fluid, Antoinette? Why not the MCP delta T of the hot fluid? Antoinette? Okay. Kaya ang mass flow rate ka cold miss ang given. Very good. Kaya wala ta mass flow rate sang hot water that was used as the heating medium. What we're given is the mass flow rate of the cold water. So that's the reason why you're using MCP delta T of the cold water. So in this case, the mass flow rate of the cold water is, pila to ganing mass flow rate given in the problem? You have 2.52. So you have here 2.52. It's okay to use the CP of water, which is 4.187. And the delta T of the cold fluid. So delta T for the cold fluid is, you have this one, 54.4 and 21.1. So 54.4 and 21.1. So in the process, you get the U sub O for the orientation 1, 2. So what is our U sub O? Alex, what's our U sub O, Alex?
Oh, wait lang, miss.
So is it 1.30 watt per square meter per Kelvin? So 54.4, we subtract 21.1 and multiply it with 4.987 and 2.52 divided by 29 and 9.30. So my answer
Yes,
is,
miss.
so 1.30, okay? So the only difference with letter B is that you're going to use a different figure. So this time your orientation is 2, 4. So using the same Y and Z value of 2 and 0.352, you're going to go back. We're going to go back to our slide for the 2, 4 orientation. So this is for the 2, 4. So for the 2, this is the 2, and for the 3.52, okay, we go up. This is 0.35. Go up 52 somewhere here. Somewhere here. If I'm going to read it, somewhere here. A little bit higher. So 0.93. Okay. So that's my approximation for the FT. More or less 0.93. Hi. So I'm using this figure for the 2, 4. Your FT then is 0.93. Okay, so you will repeat the same procedure that's done with A. Your delta T mean is equal to
Miss,
yes.
excuse me, miss. Ang sa UO, bala miss how, ang sa
Ah,
Q,
ah,
sang cold nga water. Hindi siya
ah.
miss pag i-convert miss. Kaya naka-kilowatt pa siya miss.
Kilowatt ang anong naka-kilowatt?
Ang sa Q, nga MCP delta T, sang cold.
So this one is in kilogram per second. This one is in joule, right? Per kilogram Kelvin. This one is in Celsius. So ano kung i-convert pa? Your 4.187 is in kilojoule. Okay. This is in kilojoule. You're correct. Kilojoule per kilogram Kelvin. This one, this side. So this should be multiplied to, since this is in kilojoule, this side is in joule. This should be in joule because we want to answer in watt. Then this should be multiplied by 1,000. Okay, thank you for that, Kyle. So you have to 1,000. So this would be multiplied by 1,000. So 1.3 times 1,000. So that would be 1,300. So I'll just place it there and then place this as the comma. 1,300 watt per square meter per Kelvin. So I missed that this one is in kilojoule per kilogram Kelvin. I thought it's just joule per kilogram Kelvin. Okay, so there's a need for you to homogenize your units in the left side and the right side of the equation. Is that okay now, Kyle?
Yes, Miss. Thank you.
Okay, your mean temperature would be then 0.93 times the delta T log mean. Our delta T log mean in this case is 42.326. So then your delta T mean is 39.36. So in terms of the computation for the Q, the same formula will be followed here on top. We differ only with the delta T mean. You still have the MCP delta T of the cooled water on this side. From this, you'll be able to solve for the U sub O on these 2,4 type of heat exchanger. So we'll see. I'll just change the delta T mean here based on the delta T mean that we have here, which is 39.6. So we'll have 2.52, and if we multiply it with 4187, and the difference of 54.4 and 21.1, the right side would give you a 351,356. We divide it by the delta T mean this time, which is 39.36, and we divide it by 9.30. So your U sub O in this case is 959.86. So watt per square meter Kelvin. So kindly check my value for your Q. Your U sub O is 959.86 watt per square meter Kelvin. Is that correct? So I hope everything is in place already. So any question with what we have computed here? The U sub O for A sub for letter A and B, and the delta T mean. Now you could see in here that for the 2-4 scheme, the 2 shell 4 tube sets of shell and tube heat exchanger, its delta T mean is higher than the delta T mean of that of the 1-2. Your delta T mean here is only 29, while in here it's 39.36. So the heat transfer rate for the 2-4 type of shell and tube heat exchanger capitalizes more on the delta T compared to that of the 1-2 shell and tube heat exchanger. So greater ang delta T mean sang 2-4 kaysa sa delta T mean sang 1-2 heat exchanger. Any question? So these are the processes we did. So no question? Sige, so if there aren't any question, I'll go back to our slides. And we'll proceed with the next sample problem. So this is for the 1-to-1 shell, 2 sets of tube type of heat exchanger. So number 2. So water flowing at a rate of 0.667 kilogram per second enters a countercurrent heat exchanger. So this time your heat exchanger is already mentioned at 308 Kelvin and is heated by an oil stream entering at 383 Kelvin at the rate of 2.85 kilograms per second. The Cp of the oil is given as 1.89 kilojoule per kilogram Kelvin. The overall heat transfer coefficient is 300 watt per square meter per Kelvin. And the area available is 15 meters squared. Calculate the heat transfer rate and the exit water temperature. Okay? So please take a picture of this particular problem before we try solving it in our Jamboard for ease of access for us. Okay. 1, 2. Then we'll go to the Jamboard. Okay. So we'll pause the recording for just 2 to 3 minutes. Class, I just need to drink water. I come back after 2 to 3 minutes. Or we can have a 5-minute break then. My time here is 4:50, so we come back 4:55. So for our given, first we need to note that we are given a countercurrent type of heat exchanger. And for our water that is to be heated, here are the given info. So its mass flow rate is 0.667 kilograms per second. And it is entering at this particular temperature. So inlet temperature of water is 383 Kelvin. Now it is to be heated by oil. So we'll have our heating medium as the oil. And it has a mass flow rate of 2.85. That's for the oil and the Cp. So for the oil, we're given the Cp to be 1.89. So kilojoule per kilogram Kelvin. Okay. So 1, 2. By the way, our water's inlet temperature is not 383. This is 308 only. So 308 Kelvin. For the oil, its inlet temperature is 383. Okay, so I'm counting the given information. So we have the mass flow rate, we have the inlet temperature of the water, we have the inlet temperature of the oil, we have its mass flow rate and its Cp. Then we're given the U, the overall heat transfer coefficient, which is 300 watt per meter squared per Kelvin. And then the area, the heat transfer area, which is 15.0 meters squared. Okay, so we are to determine so in the problem, it says you are to determine the heat transfer rate and the exit water temperature. So it's asking for the water outlet temperature. So I will place in here water inlet temperature. And for this one, oil inlet temperature. Okay. So this is a problem that tells you right away that there is no way that you're going to use the formula UA delta T mean. there's just so many things that will inhibit you or that will prevent you from using such a particular formula. Number one, all outlet temperatures are not known, that of water and that of the heating medium, which is oil. And then, second, there was even no mention about what type of shell and tube heat exchanger is given. Is it a 1-2, a 2-4, a 1-4? So that's not mentioned. So there's no way that you're going to have a UA delta T mean problem here. So since all outlet temperatures are not given, so in this case, you will really be using the effectiveness, the heat exchanger effectiveness epsilon. That way you can solve this problem. So we start solving the problem by writing the formula that we will be using the effectiveness method, because you know for one that this one could not be solved using the temperature correction factor or the delta T mean formula. So your Q here in terms of effectiveness is to be solved using the formula. What formula are you going to use? Mel? If you're going to use the effectiveness method, what formula are you going to use? Epsilon C minimum for our QML, that would be inlet temperature of the hot
Times
fluid.
C minimum times times HI minus CHCI.
Sige, okay na Mel. Sige, mute na. Kaya daw hindi naka-concentrate with the background there. So you have this formula. The effectiveness, the C minimum, the THI, and the TCI. Now, what do we know so far in this formula? We know the hot fluid temperature, that of the oil. We know the cold fluid temperature, that of the water. The C minimum can be solved. Okay, we know C minimum could be solved using MC of the cold water in this case. This one is unknown, the effectiveness. So since this is not yet complete, we just have it labeled as equation 1. And since we have C minimum here, we might as well solve for C minimum. C minimum is actually the MCP of the cold fluid. Now, the mass of the water as it enters is, what's the mass of the water? Let's see. So you have 0.667 kilograms per second. Now, if you're going to read the sample problem of John Kuplis, he needs to average the outlet temperature of the water with the inlet temperature to get the CP at that average temperature. And if you notice, we don't have the outlet temperature of water. So before we can solve for this C minimum, we need to assume. So this is a problem which needs you to assume the outlet temperature of the cold water. Now, so you have to make banta-banta. You just have to guess what is it. And then at the latter part, you need to check whether your guesswork is correct or not. So let's say our outlet temperature here, just let's say for example, what's our inlet temperature? So water is at 308. And then the oil is going to be at 383 inlet. So this is counter current. So more or less, our outlet temperature of water will be lower than this one because they're going to face each other in the diagram. So then, we'll assume something like, for example, we'll assume a TCO, assuming that this is equal to 365. Okay, what's our unit here? Kelvin. Okay, so at this 365 Kelvin, the TCI and the TCO should be average. So that would be 308 plus 365 divided by 2. What's the answer for this? 308 plus 365 divided by 2. So that would be 336.5 Kelvin. At this particular temperature, the average of the inlet and outlet temperature of water, you get the CP of water. So CP at 336.5 Kelvin. Can you look that up? What's the CP of water at 336.5 Kelvin? There's a corresponding appendix in John Pupils for that, where it could be readily read. Properties of water, liquid water. So at 336.5 Kelvin in Celsius, so I have it here. So there's a need for us to interpolate. Can you please find that particular CP? So my values here, I'll give you the values. I have the table here. This is your temperature in Celsius. This is your CP in kilojoule per kilogram Kelvin. So I will just place here the value so you can determine. So we'll have 338. Oh, sorry. Our value, by the way, is, I need the value, 336.5. So if it's 336.5, you will have it in between 311, 336.5, and 338.8. So the CP for 311 is 4.183. We need this CP here. In here, we have 4.187. So actually, if you don't want to go through the trouble of using this method of averaging the inlet and outlet temperature, the answer will not really that greatly vary. But nonetheless, since I have written it here, what's the CP? Can you please solve for the CP? 336. 4.186. Sige, thank you. So 4.186. So we go back here. And so this is 4.186 kilojoule per kilogram Kelvin. You multiply this for 4.186. So what's the value in here now? What's the C minimum value? 4.186 multiplied to 0.667. That would be 2.792. Okay. Now we solve for C maximum. C maximum is equal to MC of the oil. So the mass flow rate of the oil is 2.85 and its CP is 1.89. So you have 1.89. What's the value for this? 1.89 times 2.85. 5.387. Correct, Kyle. So in this case, your C minimum is then really less than C maximum. So you can proceed with the C minimum over C maximum ratio. So your C minimum, how much was that? 2.792. So we divide it by 2.792. Your answer is 0.51. Okay? Your C minimum, which is 2.792, you divide it by C maximum, which is 5.387. So this is your C minimum, C maximum ratio. So here in our formula, we already have the C minimum, so we can get the effectiveness. Now, where do we get the effectiveness? So based on our diagram, I'll go back to our PowerPoint presentation. So this is the diagram that we're going to get the effectiveness. Sorry. This one. Okay, counter current flow heat exchanger. You have the NTU here. And you have the ratio. So still we need to find the NTU, the UA over C minimum in this case, before we can use this graph here. So I'll go back to the Jamboard because we still don't have the NTU. Where is it? Okay. So that's your C minimum, C maximum ratio. So we'll have the NTU. The number of transfer unit is UA over C minimum. Oh, is that it? I'm sorry, class. It was my connection. Okay, so where was I? Wait, class. Okay, I will share again. So you have here UA over C minimum. So your overall heat transfer coefficient, okay, your overall heat transfer coefficient U is given to be 300. So this is 300. The area is 15. And you have the C minimum. So our C minimum is 2.792. So from here, you'll be able to get the number of transfer units. So that's 15 divided by 2.792. Okay, wait, class. Why is the answer so big? 300 times 15 divided by 3.792. Okay. Your overall heat transfer coefficient is in watt per meter squared Kelvin. Your area is in meter squared, so that's okay. Your C minimum is in kilojoule, so we need to divide it by 1,000. So we divide by 1,000. Our answer is 1.186. So this one, class, we need to divide this by 1,000. We will continue here because this one is in kilojoule. So we need to convert it in joule because your U is in watt. So your answer is 1.1867. So please take note of the NTU, 1.18. And for the ratio of C minimum to C maximum of 0.51. We go back to our graph here. So your NTU, you just annotate, which is 1.18, 1.5, 1.75, 1.18. You go up until you reach, let me just transfer this. You go up until you reach 0.5 or 0.51. 718, 75. 1.75, 1.17 here. 1.5, 1.75, somewhere here, probably here. So you'll be able to get now your effectiveness here. So more or less your effectiveness is, this is 0.6, this is 0.7. So more or less it's 0.75. Okay? So if it's 0.75 based on my reading, so my reading could be different than yours. So we go back to our solution. So you'll have 0.75 here. Here. So from 1, Q is equal to 0.75 times, so that's your effectiveness, times the C minimum, which is 2.792. And we have the difference of the two inlet temperatures, 383 and 308. So can you please solve for the Q? So this 2.792, this should be in kilojoule. So your answer here is in kilowatt. .75 times 2.792 times the difference of 383 and 308. So that should be 157.05 kilowatt, or this is 157,050 watt. So for your Q. Then how do you check whether the assumed outlet temperature is acceptable? So MCP delta T again. So we assumed a temperature, outlet temperature of, what's our assumption? 365. So we will check if that particular value is acceptable. So this Q of 157,050 watt is actually equal to MCP of the cold water. So MCP, so we'll have the C minimum, or rather we'll have, where is it? This one, the C minimum of the cold water, which is 2792. So I'll just multiply this by 1,000. So that's 10 raised to 3. We have its outlet temperature minus its inlet temperature of 308. Can you please solve for the outlet temperature? Check if I have the same answer as what I'm going to solve here. So my answer here is 364.25 Kelvin. Yeah, thank you, Kyle. So this 364.25 Kelvin is very near to our assumption, which is 365 Kelvin. So then since it's very near to our assumption, then this is our answer for the heat transfer rate. And this is our answer for the outlet temperature of the water. So if I labeled it as T with the subscript WO, so then we'll make it consistent. We'll have this as W. Okay. Any questions so far to what we have done here on the second sample problem? So you use the effectiveness method because we don't have the outlet temperatures. we don't have the orientation of the shell and tube heat exchanger. Okay? But what we do know is it was specified that we have a countercurrent flow for the heating medium and the fluid to be heated. So any questions so far? So Nat?